Okay, so Tony, thanks for inviting me to this webinar series and for giving me the opportunity to talk about Corpus application in forensic computational linguistics. My gratitude is, of course, extended to all the attendants. I hope you're keeping safe, by the way. And I would like to highlight the importance of these kind of online events to spread research in the field of corpus linguistics, especially in the context of the present worldwide health crisis. Besides, I'd like to congratulate Pontifical Catholic University of Sao Paulo on the 50th anniversary of LAEL. Okay, so without further ado, I'd like to set the grounds of my talk on the concept of linguistics as a science. First of all, it is important to bear in mind that linguistic methods must be tested by experiments, and the great advantage brought by the fact that nowadays some linguistic methods can be automated in software. That is great. As for corpus linguistics, it involves several disciplines, as for example, linguistics and computer technology, and can be applied to different linguistic aspects. For example, any level of language analysis and any focus of language use. Leaving theoretical controversies aside, researchers seem to agree that corpus linguistics provides an objective view of language that overcomes a single scholar's introspection by the systematic examination of a group of text, a corpus, used to find the answer to a research question related to patterns of language in use. Corpus linguistics approaches are based on two main principles, as you may know: empiricism and technology. As for the former, corpus linguistics is essentially empirical. This means that it explores language in context, or the performance of language, recalling the Chomskyan distinction between performance, what people do linguistically, and competence, what people know implicitly. Leach, I'm sure you know him, remarked that corpus linguistics examines a question of performance, of language in use. The analysis is therefore based on observation and experience, from which theoretical principles can be formulated. In this sense, it is bottom-up, and regarding technology, nowadays we should not understand corpus linguistics without computation. Basically, the adequate use of language technologies allows testing without the influence of the researcher's preconceptions. In sum, computation is key to corpus linguistics, I think, as it contributes to a more reliable analysis. Besides, it allows the handling of huge amount of data, huge amount of text in a quick and replicable way. Thus, corpus linguistics is to be framed within an interdisciplinary and integrated view of language research. So, regarding forensic linguistics, specifically, it is a fairly recent field, but it has evolved significantly over the last 2 decades. Currently, it is a very broad field, and it's not my intention today to cover each and every issue in the area, but to present the branch where we work on: forensic computational linguistics. In this branch, forensic linguistics uses tools from linguistics, corpus linguistics, and computational linguistics to solve forensic issues. So, instead of considering forensic linguistics as a separate field, we prefer to bring tested methods from different fields of linguistics as a science to the forensic setting. So forensic computational linguistics was developed out of linguistic theory and computational linguistics. In this line of research, a trained linguist has the expertise, and the methods adopted are reliable when they have been tested on known data, that is to say, ground truth data. The successful innovations in forensic science come from outside the forensic community, in our opinion, from standard procedures in a non-forensic science. And here you're provided with some examples. Forensic toxicology from chemistry, forensic DNA identification from paternity testing, forensic accident reconstruction from physics, and, in our case, forensic linguistics from computational linguistics. In this field, it's especially important for corpus linguists that they follow standard corpus linguistics procedures when they work in the forensic setting. For instance, word frequency can be presented as a raw count, but this is not as useful as the relative or normalized frequency of the word in relation to the entire word count of the corpus. And I'm sure you're acquainted with these concepts. When the relative frequency is calculated, corpora of different sizes can be compared. Thus, raw counts are hardly ever used in corpus linguistics, since texts are almost always of different sizes. The second example would be corpus annotation. Corpora are usually tagged or marked up with different sorts of information. They can be tagged at a phonological, morphosyntactic, or semantic level, for example, focusing on boundaries, or suprasegmental elements in the case of phonology, part of speech and word categories in a morphosyntactic analysis, or in lemmas and semantic fields at a semantic level. In order to improve the accuracy of an automated approach, a semi-automatic computer-assisted approach is desirable. The semi-automatic approach, using human experts to correct any errors of automatic annotation, is especially recommended when there is a justification, let us say, based on the use for which the corpora is designed. And that is the case of forensic uses. So in these fields, we have to apply regular procedures like checking to make sure the software tagged properly, for example. Not necessarily because the software is faulty, but simply because even the best commercial post taggers in the world have an error rate of about 3-4% or whatever. In order for forensic linguistics to serve its purpose of providing linguistic evidence in court, the discipline requires the series of scientific standards mentioned before, because it makes it reliable and replicable. As stated by Dr. 𝗏𝗏𝗂𝗏𝗏, standards for forensic computation and linguistic methodology include that forensic linguistics provides an empirical analysis, that it is grounded in linguistic theory, and that can be replicated. That is important in science in general. Dr. Malcolm Coulthard advocated for the use of corpus in forensic linguistics, given the possibilities that the empirical exploration of corpora can provide in terms of evidence. He states that any improved methodology must depend to a large extent on the setting up and analyzing of corpora. Indeed, Dr. 𝗏𝗏𝗂𝗏 developed the first specific corpus for forensic authorship identification so that methods can be grounded in empirical analysis. It was funded by the United States Department of Justice and available to researchers who meet research proposal standards. And here you're provided with 𝗏𝗏𝗂𝗏𝗏 writing sample database. And these are the 10 topics or the 10 tasks proposed for participants. As in linguistic research, it is crucial to control intervening variables. The topics proposed to all the participants were the same. Controlling the topic tests the ability to differentiate authors, even though they are writing about the same topic. Each author is represented in about 2,000 words. And as you can see, the tasks evoke different text types and communicative purposes, different registers of formality, and different levels of emotionality, like the description of a traumatic event, the angry letter, for example, or the letter of apology. As a general rule, forensic linguistic issues are framed within one of the 4 categories of inquiry in investigative and legal settings, what we call the 4 corners of forensic linguistics. Number 1 would be the identification of author, language or speaker, then intertextuality or the relationship between different texts, text typing or classification of text types such as threats, suicide notes, or predatory chat, for example, and linguistic profiling to assess the author's dialect, native language, age, gender, and educational level, for example. So today I'm presenting some examples of forensic computational linguistics in 2 of the corners presented. Text typing with some approaches attempting to answer the question, is this truthful or false? And number 2, author identification. Well, so within this corner, it is worth noting that deception data can be experiment in lab versus real life experience, and that is important. This would classify different corpora for this purpose, into low-stakes deception, where no harm can be done. It is well known that people lie in social situations all the time without intending harm. In Albert Freud's words, deception is a social lubricant. And secondly, we can find high-stakes deception, real life, where real-life damages are possible and even likely. Another important issue would be the importance of working on ground truth data that are forensically feasible. Ground truth data means data that we know what the correct answers are. So for deception detection, we need data where we know documents are true or false. When a method is tested on ground truth data, we can accurately report its error rate, and that is crucial in science. So within this corner, we'll review some tools for automated deception detection, or as I prefer to name it, computational classification of written statements as true or false. The first group are aimed at the automatic extraction of lexical features for different purposes, whereas the second group includes software specifically developed for linguistic deception detection. First, the linguistic approach in LEUC, in linguistic inquiry and word count, is very similar to content analysis. In line with the general inquirer, the first computer system for content analysis. One important difference between LEUC and the general inquirer is that LEUC focuses on the word as the unit of analysis, while the general inquirer is based on the sentence. But both LEUC and the general inquirer relate linguistic text to other categories of cognition. LEUC was developed in English to provide an efficient method for studying psycholinguistic concerns, and specifically the categories used were related to standard linguistic processes, psychological processes, relativity, and personal matters. A detailed description would be offered later. And by the way, I provided you with some interesting references at the very end of my talk. It has also been adapted and translated into more than 10 languages, including Spanish. It provides an effective tool for studying the emotional, cognitive, and structural components contained in language on a word-by-word basis, as we've said. So over the last few years, it has been widely used in fields like sentiment analysis, forensic linguistics, and psycholinguistics. Third, we can find this tool, 𝗵𝗃, currently in progress at the Department of Computer Science of my university. It has been built on a similar technology. The main two differences from LEUC are that it includes a linguistic basis of European Spanish, 𝗵𝗃, and that is great for us, in Spain, and several categories that are not word-based. Like LEUC, the input is a set of natural language texts, and the result is a vector consisting of different features. Thus, it's especially appropriate for automatic classification experiments, as the resulting values can be used for the training of different machine learning classifiers. And then the software specifically developed for linguistic deception detection, like 𝗲𝗿 or 𝗲𝗏, will be presented in a few minutes. Well, so here you are presented with an experiment we conducted in 2013. This is a brief description of the corpus used for the experiment. The corpus collected in English by 𝗵𝗃 and 𝗏𝗏 was used as a model for replication. And we asked 100 participants to write on these three topics. They had to voice their true or real opinion on the matters in 4 or 5 sentences. Then they had to express exactly the opposite of their opinion, explicitly lying about their true beliefs. So the corpora do not contain spontaneously produced language, but the Hawthorne effect was minimized by not explicitly telling their participants the ultimate aim of the study. And besides, a reward was provided, and it provided medium motivation for the participants because they were assigned with the tasks as an exercise for extra credits in the course. Well, here you are provided with the 4 broad dimensions, LEUC, the tool used for that specific experiment. And this tool has been used for exploring the relationship between language and some issues like state of mind, mental health, or truth value. Right, this is the first dimension. As can be seen, some of the categories are the sum of others, as the LEUC dictionary generally arranges them hierarchically. The lexical items included in the lower level category, these ones presented in white, are also included in the superior categories, here in purple, both in purple and in red. For example, these categories, first person singular and first person plural, are both subsumed under total first person and at the same time under total pronouns with the rest of them. However, in classification experiments, the use of all the categories at the same level would result in redundancy, which may yield biased results. This is what happens when you mix up all, these different levels of analysis. And in order to avoid this, there are two options. Either removing the hierarchically superior categories, or keeping them and leave the inferior categories out. In our case, the first option was selected, to keep the most specific categories. This feature is especially obvious in the second dimension of LEUC, if you pay attention to this table, because they contain classes related to psychological processes because of their hierarchical structure. For our experiment, only categories in black, in this case, have been kept. Well, this would be the third dimension by Pennebaker-Itali relativity, including this kind of features. And this would be the fourth dimension, including personal concerns in general. Well, although there are some stylometric features within the LEUC linguistic dimension, the first one, for our analysis, some further stylometric categories not previously explored have been included. They were obtained with wordsmith tools, and the first of these variables is the standardized type token ratio. The non-standardized version of this ratio was included in the LEUC linguistic dimension, but it has been proved to be too size-dependent as an index of lexical richness, so it has been replaced with the standardized version. The next variable is the ratio of the total number of sentences to total word count. A similar ratio was then calculated with other possible word lengths from 1 letter to 7 letters. And finally, we've got the ratio of complex words to total word count, considering those words longer than 7 letters, as this is the general agreement in the study of readability indexes. So once we've got the categories extracted for every text, a framework based on a classifier using a support vector machine has been used. This is a set of related supervised learning methods for the analysis of data and pattern recognition. Well, with this kind of supervised algorithm, examples are represented as points in space, as you can see here. And a hyperplane or a set of hyperplanes has been successfully applied in many, for the creation of the separation of these different examples, falling into 2 different categories. Well, and this technique has been successfully applied in many text classification tasks, not only in forensic linguistics, of course. Well, and I think it's worth noting that an object's characteristics are also known as feature values and are typically presented to the machine in a vector called a feature vector. Well, here you are provided with a diagram of the procedure in which a 10-fold cross-validation was performed for each classifier. This is a technique for assessing how the results of a statistical analysis will generalize to an independent data set. It is mainly used in settings where the goal is prediction, and one wants to estimate how accurately a predictive model will perform in practice. In tenfold cross-validation, the original sample is randomly partitioned into 10 equal size subsamples. Of these 10 subsamples, a single one is retained as the validation data for testing the model, and the remaining 9 subsamples are used as training data. So the terminal attributes of each Liu dimension were used for training. For this purpose, the 𝗬𝗂 library was used, and just in case you don't know it, it's a suite of ML of machine learning software written in Java with a linear support vector machine using the default configuration set by the tool. Precision and recall have been calculated, and then the F value, their harmonic mean, and they have been taken as the success rate. Here, we are provided with all the classifiers. So, the machine learning experiment showed quite a successful classification of the statements into truthful and untruthful. In every case, better than chance, which is good. Overall, the most discriminating dimension on its own is linguistic processes, whereas the dimension related to personal concerns, remember it, the fourth one, yields the poorest results. It is natural that it should be so, I think, bearing in mind the considerable potential of function words, which constitutes a substantial part of standard linguistic processes. The prime importance of these grammatical elements has been widely explored, not only in computational linguistics, but also in psychology. Variations in the usage of function words have been associated with sex, age, mental disorders such as depression, for example, status, and deception as well. On the contrary, the fourth dimension is the least discriminant on its own, as we've seen. Well, these experiments, with an accuracy around 70%, yield similar results to 𝗵𝗂 𝗟𝗵𝗲𝗂, the reference study, which happened to be in English, by the way, which means that differentiating between truthful and untruthful text is possible in this controlled environment, as these classes present features that make them separable. And it is worth noting that classifiers combining several dimensions perform more satisfactorily than isolated categories. The best classifier and the worst one. Well, now from that experimental data set, we are moving to a great example of contextualized study of deception, 𝗲𝗏. This is a model for the detection of false robbery reports based only on their text. This tool, developed in collaboration with the Spanish National Police and the Ministry of the Interior, combines NLP and machine learning methods in a decision support system that provides police officers the probability that a given report is false. The impact of this tool was tested by means of an on-the-field pilot study that took place in 10 police departments in 2017, and this is considered high-stakes deception, as a false report is a crime governed by federal and state laws. It may influence the outcome of a criminal investigation, of course. In fact, in this case, the deceiver is tested, and the most interesting thing, I think here, is the use of ground truth data. Because 𝗲𝗏 was tested on a corpus of 188 false robbery reports and 134 truthful robbery reports, which is great practice, as I explained before. Empirical results show that it is extremely effective in discriminating between false and true reports with a success rate of more than 91%, improving by more than 15 the accuracy of human expert police officers on the same data set. The pilot study was so successful that nowadays it is officially used in all the national police offices in Spain. Well, let us now move on Alias Technology, a company which provides forensic linguistics consultative attorneys, law enforcement, human resources, and security teams, and whose CEO is Dr. Kārachevski. One of the modules in Alias is Witness Statement Evaluation Research, or simply WISER, a project using automated text analysis and statistical classifiers to determine the best protocol for computational classification of true and false statements in the forensic investigative setting. In one of the experiments conducted with this software, this one, 𝗏𝗏 results showed a remarkable difference between the experimental data, in which students were asked to write two narratives of a traumatic experience, one truthful and the other one false. And high-stakes data, on the other hand, actual statements from real criminal investigation with non-linguistic evidence of their veracity or falsehood. Using the same algorithm, the texts in the experimental dataset were correctly classified using leave one out cross-validation 71% of the time, while the text in the high-stakes data, in the second dataset, were correctly classified using leave one out cross-validation 93% of the time, which is a very, very good result. And this result demonstrates that there is a real difference between lies told in experimental setting, for example, in a classroom as part of a class assignment, and lies told in a police investigation. Well, here you are provided with a screenshot. These are just some of the categories used in 𝗏𝗏. And this tool uses measurements at the character, word, and discourse level, as well as the themes, as can be seen here. So one strange thing in English is that the false ones in the student essays had a lot of dentals. And then we realized that that was because the liars were claiming, no, I didn't do it, or this kind of dentals or veilers included there. So some of the themes here are discourse related and some others are content word related. And these categories weren't developed with deception in mind. That is fairly curious. But they were just categories related to Maslow, the Maslow pyramid, like physiological needs, safety needs, belongingness, and love needs, for example, apart from crime. Okay, so in a nutshell, it is very important to conduct this kind of contextualized study of deception. Of course, the use of ground truth data, as we've said, and it's also important to bear in mind that the existing tools are not infallible. And as linguists, we should keep on testing what is used in real life and trying to improve it with our linguistic knowledge. Well, so it brings us to 𝗏𝗏's, a system for linguistic evidence. And this system maintained on secured web accessible server, and subscribers access the system to import or to store linguistic data, and different types of data can be stored there, which makes it great. 𝗏𝗏's modules perform high-level linguistic analysis, and each module is tuned for its specific tasks. Okay. And then results for investigation and testimony. It includes testing on ground truth data. It produces quantitative requirements and error rates. And of course, it meets the US legal evidence standards. So this takes us to the second forensic issue I promised to deal with today: authorship identification. As Dr. 𝗪𝗂 put it in this series of webinars, the problem is that when we do authorship analysis, we cannot base our findings only or on a single marker. We need a set of markers, because the fact that someone uses a specific word is not enough to attribute authorship to someone. And the fact is that if you try to imitate someone else's writing, usually you can successfully imitate lexis, but syntax is much more difficult to imitate. And syntactic analysis involves identifying the roles that words and punctuation play in a given phrase structure or a set of phrase structures, as well as the relationships between them. Syntax is unconscious, is automatized behavior, because when we speak or even when we write, we focus on the meaning we are conveying rather than syntactic combinations. We wrap the meaning in. Syntactic analysis also takes into account the complexity of phrase structures, as explained by Battistella in his theory of linguistic markedness. And a marked phrase is simply constructed and uses words in their default or neutral form. For example, here, the professor. While a marked phrase is more complicated, requiring a better grasp of the language to construct, and is acquired later in language development, as in, for example, the Swedish professor who you met at the conference. Syntactic structures have long been a focus of research, I would say, in authorship identification, and they've been proven reliable. And those are the grounds for one of the modules in ALIAS, 𝗔𝗍𝗍, syntax-based author ID. Well, the reality of phrase structure in our cognition means that we all have this common experience of being able to finish another person's sentence. And the reality of phrase structure in our cognition is demonstrated neurologically and accepted by linguists of all schools. And another common experience would be not being able to repeat verbatim what has been said, okay? Which means that syntax degrades in milliseconds in memory. So the data analysis procedure for 𝗔𝗍𝗍, the syntax-based author ID, would be, I mean, this would be the main steps, not all of them, but I'm just summarizing them, that the known documents are analyzed for its syntactic category. They're analyzed linguistically using this method, okay? And the syntactic category could be noun, verb, adjective, etc. The combination of tags is categorized as marked or unmarked. Each document is measured for 26 syntactic features. The 26 linguistic categories are quantified so that each text has a numerical profile. The numerical profiles of the known authors are tested statistically using linear discriminant function analysis to determine if 𝗔𝗍𝗍 can differentiate the different authors in a cross-validated accuracy. And then, using that statistical model, it is applied to classify the questioned documents, reporting the error rate, as we've said before. Once again, you can see the benefits of applying statistical techniques in corpus-driven analysis, as highlighted by our wonderful host today in their 2019 volume on multidimensional analysis, co-edited by Murcia and 𝗏𝗏. So far in this presentation, we've seen some examples of application of logistic regression of machine learning techniques, and now it follows that the preferred statistical technique in ALIAS 𝗔𝗍𝗍 is linear discriminant function analysis, by the way, using IBM SPSS. Okay, so the main motivation to use this method is its accuracy for authorship ID. This syntactic method has been used in approximately 50 cases with average accuracies of or higher than 95%, which is a lot. And 𝗔𝗍𝗍 has been admitted as scientific evidence in federal, state, and military courts after evidence hearings, and has been used in Canada, Australia, and Europe. So the examples I've gone over are within the ILE paradigm, the Institute for Linguistic Evidence, which was founded in 1998 by Dr. 𝗂𝗏𝗂𝗀𝗏 as a non-profit scientific research organization. I am the director of research of that institute, and I can tell you that as a general rule, the formal applicant, if you want to become one, to ILE, is to hold master's and or doctoral degrees in linguistics, research experience as an independent researcher, and a strong interest in forensic linguistics, of course, and also a clear research proposal. On our website, you'll find further information about the institute. And here you are provided with our paradigm, including that empirical testing of method has to be independent of litigation, that the methods applied have to be grounded in linguistics, that the method is tested on ground truth data that are forensically feasible, that all known and questioned texts are analyzed the same way, that is important, by computer software whenever possible, or by protocol, okay? The data are not contaminated, that you haven't fixed the data, And the statistical procedures are in method and follow standard principles of statistics, including cross-validation. And that a conclusion or a prediction from testing the forensic data is stated in the final report and in testimony. So this would be our research agenda for the 𝗬𝗍 project. The first, I mean, with a witness statement. Okay, for this tool, our agenda would be to get some Spanish translations of alias categories and getting enough witness statements. Because if we can get 100 witness statements where we know from the police other evidence they are true or false, like 𝗲𝗍𝗄𝗏, then we could build a really strong model and method. Because currently we only have 31 witness statements, non-truth or falsehood in English. Okay? So we need to complete this corpus and also to collect some others for Spanish. And our second goal will be, it is because it is indeed ongoing research for us, formalizing Spanish marketness. Okay, the first step towards the Spanish version of alias 𝗍𝗵𝗍, already presented at the American Association of Forensic Sciences this year, before the pandemic, by the way. So we've already conducted a preliminary contrastive analysis of English and Spanish. We've measured marketness categories in Spanish, and we've performed some empirical testing of categories through a Corpus 𝗲𝗏 test. So some final remarks on applying corpus and computational linguistics into the forensic setting. Methods must be adjusted for realistic forensic use. Methods must provide an error rate of forensic data. And even within forensic science, methods should continue to be driven by research within the forensic setting. Okay, and here you are provided with some references and the materials I've used. I'll be happy to share them with you through my slides if you're interested in. And thank you very much for your attention.
Wow.